Okay, so today I'm going to review linear transformations. Linear transformations. But before I do this, I'm just going to go over some preliminary concepts that we should remember in order to get a good understanding of linear transformations. So the first concept is just a notation concept. Suppose we have our axes here, x, y, and z. In high school, we use the notation uh, I, j, and k for our unit vectors. But in linear algebra, we use the notation uh, as follows. We use the notation instead of ijk. Since we have higher dimensions, we will quickly run out of letters. So we use the notation E1, E2, and E3. So this allows us to go into, sorry, it's not K, this is Z. This allows us to go into higher dimensions. So we use the notation E1, E2, E3, etc. So that's the first concept. Now the second concept is the concept of span. So span is actually, in more simple terms, is just all possible linear combinations. So suppose we have the span of the set of vectors, I don't know, let's go 1, 1, 0, negative 1, 2, 2, 3, 0, 0. The span of this is equal to all combinations of the vectors 1, 1, 0, negative 1, 2, 2, and 3, 0, 0. And in this case, all combinations of these three vectors, since they're completely distinct vectors, would actually form a plane. So in this case, it would form a plane. Okay. But in general, the span of vectors forms a geometric object, a plane, or a 3D object, a line, etc. Another easy example would be the span of the vector 1, 1, 1. If you can think about it in terms of our coordinate axes, just to actually picture what span means, we have the vector, so we have x, y, z. Would place our 1, 1, 1, 1 vector would be here, here, here. It would be pointing this way, kind of out of the screen. So the span of that would be all combinations of 1, 1, 1, which is just equal to some scalar times the vector 1, 1, 1. You can take any combination of that. You can take 2 times that, etc. So the span of this vector would just form a line. This would be the line k times 1, 1, 1. So that's just a quick idea of what span means. Okay, so now actually let's get into the main topic of the video. So we're going to talk about linear transformations. So the general form is that we have our transformed vector t of x is equal to a times x. In other words, our transformation, for it to be linear, has to equal the product of a matrix and a vector. Okay, so keep this in mind for now. Now, you might be confused about linear transformations because, to be honest, it wasn't really explained properly in our year. But I'll try and explain it a little bit better here. So let's take an analogy of something we understand better. Let's take a calculus analogy. So say we have the input x, where x is just some number. In calculus, let's say single variable calculus, we pass it into our function f, for which we know the formula. This could be something like x squared plus 3 or whatever, right? We know the formula for f. And our output is also a number we call f of x. So in calculus, we take an input as a number, we pass it through our function, which could just an example is x squared plus 3, and we get an output of f of x. Now linear algebra, it's really the same thing. In linear algebra, we're not really dealing with just scalar numbers, but we're dealing with vectors. So what we do is we take the vector x, right, and we pass it through not our function, but something very similar, which is our linear transformation, and out comes our transformed vector t of x. So in calculus, we put a number in, we take our function, and we get a number out. In linear algebra, we pass a vector in, we use our transformation, and we get a vector out. So it takes a vector to a vector. Okay, now there's actually a couple really important properties of linear transformations. So some properties. So there's two major properties. Not translator. Sorry, bear with me for a moment. Let's close that up. So two properties is that if we take the transformation of a vector kx, so some scalar multiple times our input vector, it's equal to that same scalar multiple times our transformed x vector. Okay, so an example of this would be t of 3x is equal to 3 times the transformation of our x vector. Now the second property, and probably the most important property, is the associative property, which states that the transformation of the vector sum x plus y has to equal the transformation of x plus the transformation of y. If any of these two properties are not met, the transformation cannot be linear. Okay, and now another note, as I said, the general form is that our transformation of x, which by the way, this is a vector, it's just a notation for our output, just as f of x is a number, t of x is a vector. The general form we said was ax, so some transformation matrix A times our input vector x. The general form for A is that it's a matrix which columns are the transformed vectors E1, which remember is our transformed x-axis pretty much, our transformed vector E2, etc., all the way to a transformed vector En, depending on the dimensions of our transformation and whatnot. So in other words, if we can transform our x-axis, our y-axis, and our z-axis or whatever, we can actually form our transformation matrix. And the reason for this is because any vector can be represented as a sum of the unit vectors, right? So say we have the vector 3, 4. I think we can all agree this is equal to 3e1 plus 4e2, right? It's like, or 3i plus 4j. So the general principle behind this is that once we transform using A, our output has to be some sort of combination of the transformed x, y, and z axis, the transformed unit vectors. These are the transformed unit vectors in a sense. And so the output, in order to be linear, for the concept of linearity, the output vector still has to be a combination of the unit vectors. So in the input vector, it's a combination of the unit vectors. In the output vector, it's a combination of the transformed unit vectors. So that's the general theory behind that. Okay, and so another thing to note here is something called the image. So we talked about this in linear algebra. The image of A is equal to the span of the columns of A. And as I just mentioned, the columns of A are the transformed unit vectors. And so why is it called the image? Because the span of the columns of A gives all possibilities, all linear combinations of the transformed unit vectors. And the transformed unit vectors form a basis for the entire transformed subspace. So the span of all these columns here is, in a sense, what the transformation looks like. So what the transformation looks like, or i.e. image, the image or the picture of the transformation, what it actually looks like geometrically. That's why we call it the image. It's a little fun fact. Okay, so this probably don't really need to know this probably for process control, the image, but it's just something to try and connect the dots a little bit from stuff we've learned previously. Now to finish up the video, I'll see a quick example of a linear transformation, and hopefully this will be sufficient quick review for linear transformations. So suppose we have the transformation t of x is equal to 1, 0, 0, 3 times x. Now remember, this here, let's use blue so it's not so monochromatic. This here is our a, right? And this is our x. So t of x equals ax. It's still the same general form. So suppose we want to know what the transformation is doing. Now I'll agree with you that if you see this, you probably have absolutely no clue, and neither would I until I write it out what this is doing to x, right? You just see a bunch of numbers in a box. Okay, but let's break this down a little bit. So what this means is that the transformation of our vector x, which I'll write out in component form, x1, x2, is equal to our matrix 1, 0, 0, 3 times our vector x1, x2, which is equal to x1 plus 0x2 and 0x1 plus 3x2. So if you rewrite this, you will see that the transformation of our vector x1, x2, we pass this vector x1, x2 into our transformation, or our function, and we get, as an output, we get the vector x1 and 3x2. Now, at this point, we can probably get a good understanding of what the transformation is doing. So we pass in the vector x1, x2. Let's look what happens to the x-coordinate. The x-coordinate stays the same. x1 stays as x1. But x2, our y-coordinate, gets multiplied by 3. So what this transformation, and there's lots of transformations, remember there's reflections, rotations, projections. This transformation here is a dilation or expansion, whatever you want to call it, by 3 in x2. Okay, so just to continue here on our linear transformation, we talked about linear transformation represented by the matrix 1, 0, 0, 3, which is our A, and that represented a dilation or expansion by 3 in the x2 direction. So to understand what this might look like geometrically, to take it one step further, let's pick some input vectors. I'll just call x1, say x1 equals to 1, 2, and we'll take, x2 equals to 1, 0. We'll take another input vector, x3 equal to 0, 1. And by the way, this vector here is the same thing as e1, and this vector here is the same thing as e2. So now let's do a quick sketch of what this may look like. So we have our x2 axis here, or a y-axis. We have our x1 axis here. And so say we start with the vector 1, 2. So our vector 1, 2 would be roughly something like this. This is our x1. Our initial vector x2 is 1, 0. So that's this vector here. And our 0, 1 vector is here. So this is our x3. This is our x1 vector, and this is our x2 vector. Perhaps I shouldn't have picked x as a variable to represent the vector, but it's not a big deal here. Now to compute the output, we want to use the transformed output vector. We want to use our recipe here, which is that the x1 coordinate won't change, but the x2 coordinate gets multiplied by 3. So let's use a different color here. Let's use green. So if we take the transformation of 1, 2, this will be equal to 1 and 3 times 2, which is the vector 1, 6. If we take the transformation of the vector 1, 0, which is our x2, we will get the x coordinate staying the same, and the y coordinate is 3, gets multiplied by 3 based on our transformation here because it's scaled by 3. So this is also still 1, 0. And the transformation of our vector 0, 1, the 0 won't change, but the 1 gets multiplied by 3. So we get the vector 0, 3. Okay, now let's sketch this on our plot here. So here's our x1. Our t of x, looks like I mislabeled that, my apologies. This would be x1, and this is x2. Okay, so to continue, our transformation of x1, which was our 1, 2 vector, is the 1, 6 vector. So it would be 1, and then we'd go up to roughly here. It's a little bit off the grid here, but this would be our transformed x1 vector. Now let's look at our transformed 1, 0 vector. So we start at 1, 0, and we end at 1, 0. So this is our t of x2. And if we look at t of 0, 1, we get 0, 3. So we end up right here. And so as you can see, in this case, only the x2 coordinates changing. So this is basically what the stretch looks like. And also something to notice is that the vectors here, 1, 0, and 0, 3, are precisely the columns of our matrix. And that is because this is really just t of e1, and this is really just t of e2. And if you look here, we said t of e1 is the first column, and t of e2 is the second column. That is the definition of the matrix for a transformation. Okay, and now let's just do, let's say one more example. So we did a stretch by a factor of 3 in the x2 direction. Now let's say we want to determine the matrix for a reflection. Now I'm going to exploit the fact that A, like I said before, is equal to the transformed basis vectors as their columns. T of E2. E2. So that is the columns of the matrix A. So say we want to reflect in the x2 or the y axis, and we want to represent this a matrix. To represent this, we can use the properties I've discussed already to actually develop this without needing to memorize the formula for a reflection matrix. So let's sketch what would happen, right? So this is our x2 axis here, x2, and here's our x1 axis. We said we want to find a transformation that reflects in the y-axis, right? So we have some input vector here, and the output would be, ideally this would be our input vector. Let's call it I1 for input. This would be our input vector 1, and we know that it should end up reflected in the y-axis. So this is basically what we're doing. We're reflecting in the y-axis. But as we said, if we can find the transformation of E1 and E2, we can easily find the matrix. So let's think about what would happen if we took the vector E1 and transformed this by rotating it, or reflecting it, sorry, in the y-axis. I think we could all see that if we were to reflect in this line here, E1 should end up here, right? This should be our transformation of E1 if we want to reflect in the y-axis. And similarly, if we take a vector E2, and we reflect in the y-axis, we should not get anything different. It should stay the same because it's already on the y-axis. So E2 should actually equal a transformation of E2. So if that's the case, then this means that T of E1 equals T of E2 equals, we said that T of E2 is equal to E2 because it did not change as around the y-axis. So that means T of E2 is equal to the vector 0, 1, whereas T of E1 started off as 1, 0, but it ended up by reflecting the y-axis, so the x-coordinate becomes negative. So this E1 gets transformed into the vector negative 1, 0, or negative E1. That means that A, which is T of E1 to T of En, that means that this matrix has to equal negative 1, 0, which is our T of E1, and the second column would be T of E2, which is 0, 1. So therefore, the matrix negative 1, 0, 0, 1 represents a reflection in the y-axis as desired. So that's how we can derive transformation matrices. I hope this was helpful, and in the next video I will talk about determinants. Thank you.